So the topic of today's lecture is analysis of algorithms. So let's dive into it. Analysis of algorithms is a part of a complexity theory which tells us about how much resources our algorithm will require to solve the specific computational problem. We can also say that this method can be used to predict the behavior of the program, that is, to understand theoretically without implementing it on a computer or writing the program and running it. We can predict how much time and space the program might consume when it is run on a computer, and it will determine it irrespective of the device, which means that it will be common for all devices rather than just a specific computer or a specific device. Let us take a deeper look with the help of this example. On the screen, we have an example which shows a problem, sum of n natural numbers. The problem is such that the user provides an input as n, and the program is supposed to find the sum of numbers from 1 to the digit n as given by the user and return it as an output. The function, that is the problem given to us, is being implemented using three different methods. The first method uses a direct formula, that is n multiplied by n plus 1 by 2, which is a direct mathematical formula to return the sum of n natural numbers. The second method here is implemented with the help of a for loop. A for loop, or loop in general, is a conditional statement that will keep on repeating itself until the given condition is satisfied. For the specific method, we initialize a variable or a number named sum from 0, and we use a loop to keep on running itself, to keep on incrementing the value and adding it to sum. The loop here runs from I is equal to 1 to I is equal to n, which means that it takes 1, then adds it to sum, which is 0 at a point, then it changes the value of I to 2 and then adds it to sum. The value of sum is converted to 1 due to the previous loop iteration. Then it keeps on repeating until it adds n, and the given condition that until and unless I is less than or equal to n is satisfied, the loop stops running and then returns the value of sum, that is the entire sum of natural numbers from 1 to n. The third method is a more detailed method, a more complex method, which rather than adding numbers from 1 to n by adding 1 plus 2 plus 3 plus 4, it adds it in this manner: 1 plus 1 plus 1, that is 2, plus 1 plus 1 plus 1, that is 3, and so on until it adds repetition of 1 as n. So this method is more complex. It uses two for loops called nested loop, which is a loop inside a loop, and it uses this method to just increment the sum values so that it keeps on adding ones to itself. This method at the end again returns the value of sum as an output to the user. Now pause the video for a minute and think about it. Which of the three methods will be the fastest to implement? I hope that you have thought about it, and the correct answer for this is method 1, of course, because first method uses a direct mathematical operation, which is just a multiplication and addition of numbers to give us the solution, while the second method uses single for loop to continuously run and consume some space, some time. The third is more advanced method and uses much more time and space to run two for loops. So why is that a single function, a single program that we wish to write can be written in multiple ways, returning us the same output, giving us the same output, and still we have a method which is the best to use, a method which is the worst to use? The answer to this is given by a different topic, a topic which comes under the umbrella of analysis of algorithms. Asymptotic analysis is a method, it is a way to evaluate the performance of the algorithm, to evaluate the time complexity and auxiliary space of the algorithm by focusing on its growth rate rather than how the algorithm is written or what function it implements or on which device it is done. It uses a single variable, that is the input size or the growth rate, to compare the algorithm with others. So as written on the screen, asymptotic analysis is a way to evaluate the performance of an algorithm by focusing on its growth rate as the input size becomes large. and it focuses at how the algorithm scales when the input size is increased. It would not depend on the hardware or the programming language, because this analysis can be done without even writing codes, and it thus helps us to compare the algorithms as the input size grows. Let us take a look at asymptotic analysis with the help of the examples that we looked at before. For example, here we saw that the first function was just uses a mathematical operation, one being multiplication, other being addition, and one being division, which would not consume a measure of a time. The second operation, in which we used a loop, would run n times. How and why? First time the loop will run when the value of I will be 1 and it will be added to sum. Second time it will run when the value will be incremented to 2 and added to sum, and thus will be running till the value of I become n. So the entire n time the operation is run. So if we see that thing operation by operation, the first operation that we performed, that the value of sum is equal to 0, is a single operation. It's a constant time taking operation, while the operation of the loop that we have done is a operation which is performed n times, as we saw before. The sum operation, on the other hand, still would take constant time because it's a general mathematical operation. So overall, the method 2 will take some level of constant times. So as the input size of n will increase, for example, if the input is given as 1, the loop will run only once. If input size is 2, the loop will run twice. If 3, then thrice, and so on until n times the loop will be running n times. So the growth of this program, the time taken by this program should grow linearly as compared. On the other hand, if we see the third program, first operation is still taking constant time because it's just giving a value to the variable. The outer loop will run n times because again the value of I will be incremented from 1 up till n. In the inner loop, the value of j is initialized from 1 until n. So this loop would also run n times. The similar fashion the outer loop run, and again inside there is a mathematical function that won't do much thing, it will take constant time. So overall, this operation in itself will, if given a value 1 as input, if n is equal to 1 is given as input, the outer loop will run 1 time, the inner loop would run 1 time. So 2, if we say, when 2 is given as input, the outer loop will run twice, the inner loop will also run twice, so 4. If given 3, outer loop 3 times, inner loop 3 times. But if we look at it more closely, for each outer loop iteration, for one outer loop iteration, this runs 3 times. For second, again runs 3 times. For third, again runs 3 times. So overall, if given 3 as input, it will run 9 times. And thus we see that when given input n, the entire operation is performed n square times. Thus this program grows quadratically, and this is a similar fashion. This is a way in which we can identify the growth rate of the algorithm based on the algorithm written and the input size as well. Now let us try to understand it more deeply and in more detail. For example, here we take a graph where on the x-axis we plot n, which is the input size, and on y-axis we plot time taken, that is TA of n, which is the time complexity or the time taken by the operation to run based on the input size. For example, we have a sample function named fx, a sample program or a function named fx. For input size, let's say n1, it gives us this time. For n2, it gives us this time. For n3, it gives us somewhat this time, and if we join all the points up to n equal to infinity, it might give us a graph like this. Let's call this fx. Now let's do one thing. We also have a graph which is like this. This is called f1x. We also have a graph, this is called f2x. Now as we see that as the input size is increasing, the value of fx is given to us. At a certain input, let's say n0, we see that f2x is taking less time, fx is taking more time, and f1x is taking the most time when compared to the three functions. Now if we take this function as examples and compare it with our previous sum of natural number algorithm, if I say that this function is the general mathematical operation, if this is the one with one for loop and this is the one with two for loops, it is similar in fashion, because the same operation, when given the same input size, the one with mathematical operation was faster and the one with two for loops was slower. So for the given problem, for the given function, we can say that the one which used a mathematical operation itself was the best case. It was the best case algorithm that we had written. And the one which took the most time, we can call it the worst case. It was the worst algorithm we could have written. Similarly, the one which was neither the best nor the worst can be called average case. So thus we get to know that a function can be written in three ways and can be compared in three ways based on the time it takes on the given input size. Either it can be best, it can be average, or it can be worst. Now if we look at it in more detail, for example, we take the same function, let's say fx again, which used one for loop. Now we wish to know the function fx itself. We cannot say that the function had one for loop. We need a mathematical representation for it. So on x-axis we take n input size and time taken by the algorithm on y-axis, and let us say our function f is plotted like this, fx. Now I know a certain mathematical function named gx, which can be plotted on the graph like this. Let's call it g0x. I also know a mathematical function that can be plotted on a graph like this. I'll call it g1 of x. Now if I see, after a certain point, after a certain value of input size, the function g0x always gives me a value greater than the function f of x. If you see that the difference keeps on increasing and the value at infinity will always be greater for g0x compared to fx. Similarly, after a certain input size, after a certain input value n, the value of g1x is always smaller than the value of fx, which means that by the time it goes to infinity, g1x will have a smaller value compared to f of x. And thus, what we can say is that the function g0x will represent an upper bound. The function g1x will represent a lower bound. How? The function fx is bounded between two functions, g1x and g0x. g0x being always above fx and g1x being always below fx. Thus, this can be called as upper bound of fx and this can be called as lower bound of fx. So, for example, I also have one function which is almost parallel to fx. Not exactly, but almost. So it will always be at a constant spacing from fx. And because it mimics the behavior of fx, I can call this exact bound. So using these functions, g0x, g1x and the exact bound function, we can understand the order of growth of the program, the order of growth based on the input size. For example, if I look at the specific value of let's say g0 n upon f of n, that is on input size n, the ratio of g0, that is my upper bound function, to the function I am checking at limit n tending to infinity. So here we see that the ratio of g0 at n and f at n, where n tends to infinity, is equal to infinite. And similarly, if I see for limit n tending to infinity g1 of n and f of n, it will give me the value 0, because at infinity g1 of n will have very less value compared to fn. And also if I look for the exact bound, calling it g2 of x, if I see that limit n tending to infinity g2 of n upon fn, it will give me a constant value because there is an equal spacing maintained. It runs parallel with the function fx. So based on my theory and based on my calculation, I can state that I can represent a function's upper bound, the function which is always above fx, lower bound which is always below fx, or exact bound or tight bound, which is a function running equally parallel to fx, by some notations. I can represent upper bound by a notation called O, lower bound by a notation called omega, and tight bound or exact bound by a notation called theta. These are the three notations that I will be using to show my function's upper bound, lower bound, and exact bound. And these notations are called asymptotic notations. I hope that you have understood the concept thoroughly. Thank you so much for watching the video. I'll see you in the next one.